supplemental instruction series of videos for Chemistry 121, and today we'll be discussing the different kinds of nuclear decay.
Decay?
Mm-hmm.
They die?
Not exactly, it's more like they break apart.
That's okay, I guess. I'm Smokey.
And we'll be discussing this with you today.
So apparently there's more than one kind.
That's correct.
Okay.
So, one of the first kind we're going to talk about is alpha decay. Now, when you have a nucleus, and it's typically a large nucleus, like say a nucleus of uranium, for example, often it's so large it has to break apart and emit a smaller particle, and that's what happens in alpha decay. So you have your nucleus, and then it breaks apart, and then you have an alpha particle, which is also known as helium nucleus because it has the same protons and neutrons as a helium nucleus. And then what else you have left over is a completely different nucleus that weighs 4 less than the previous nucleus. So it has 4 less total atomic mass and 2 less protons.
So basically it's like you're shrinking the big thing and you're emitting a smaller thing.
Yes, pretty much.
Okay, so what do all these letters and stuff mean? I'm kind of confused.
So, well, X is simply just a nucleus that you start with. A, of course, is mass number. Z is, of course, atomic number, if you review back to those videos.
Okay.
Then Y is just the different nucleus. A minus 4 meaning 4 less than what your mass number was before, and Z minus 2, subtract 2 from the number of protons you had before.
Okay.
And this is how you would write an alpha particle.
Okay.
Or you can write that it's a helium nucleus. Either one is acceptable.
Okay, so always in alpha decay, we're always going to go to helium? Is that the case?
Yes. Helium, and then your other nucleus is going to weigh 4 less and have 2 less protons.
That makes sense.
Alright, so now we get to the beta decay. Now this may be a bit counterintuitive at first, but it'll make sense eventually.
Okay.
So you start with a nucleus, just like last time, except usually you start with a smaller nucleus, typically, like maybe a nitrogen 15 or something like that. So what happens is that the nucleus will emit an electron, and as a result, you'll have 1 more proton, and then it'll emit that electron. That electron is also known as a beta particle.
Okay.
So you can either write it this way or this way. So notice here, the mass number doesn't change because electrons are practically weightless.
Yeah, they're so small.
But the number of protons changes by 1 in the new nucleus. And then to make sure everything balances on both sides, we don't have more on one side than the other, this -1 is put down here to essentially be our -1 number of proton because electrons are oppositely charged.
Right. So this is basically you just kind of randomly lose an electron.
Yes, for the most part.
Okay, that makes sense.
Alright, so now we have positron emission. It's kind of equal to the beta emission, but opposite.
Okay.
Because you start out with your nucleus as you normally would. Then you form your other nucleus, except this time, instead of losing an electron, you lose what's called a positron. Now, a positron is the same size of an electron, but it has an opposite charge. It's positive instead of negative.
So it's like a positive electron.
Yeah, and so your atomic number actually goes down by 1, and then you get a 0 and a +1 right here. And again, the reason that is to make sure that everything adds up to the same on both sides. So z minus 1 plus 1.
Okay.
It still adds up to z.
That makes sense.
Alright.
So Kevin, all these equations are going in one direction. I'm kind of curious, is there any way that maybe we might come across an instance where it go the other way? Like maybe the nucleus will kind of accept the helium?
Oh yes, certainly. You could accept an alpha particle. Common ones include electron or positron capture. You'll see that a lot. And if you want to deal with that, it's really just the reverse of these equations up here.
Yeah, so instead of taking one thing, breaking it up, you're taking 2 things, putting them together.
Yeah.
Okay.
And so, a note on all of this is it's basically, So all this essentially is transmutation, changing from one element to another.
Mm-hmm.
And as you may or may not know, that was the ultimate goal of alchemists of old, to change one material into something completely different.
Like lead into gold.
Yes. But thanks to modern science, we can actually do that now.
Yeah.
Isn't that amazing?
That is pretty amazing. Cool.
Now, there is one more form of radiation you'll need to know about, but you probably won't be using in any equations. That's gamma radiation, which you may have heard about.
Mm-hmm.
That's essentially when an excited nucleus emits a gamma ray, which is a type of electromagnetic radiation. It's essentially a form of light.
Mm-hmm. Okay.
So that's all you really need to know about gamma radiation.
So it's like an atom kind of magically twinkling or something.
Yeah.
That makes sense. So and stars do that, isn't that right, or something?
Yes, exactly.
Okay.
Stars emit gamma radiation. Lots of things emit gamma radiation.
Cool. Nuclear decay is pretty awesome.
Yes, it is.
Ah,
It's
wow.
quite fun. In fact, you know what? I'm going to practice some of these right now.
I want to go do this in the lab, man. What are you talking about?
Yes, that's a good idea. Let's turn lead into gold.
Yes.
All
See
right.
you later.